My name is Pravalika Putalapattu, and I'm a senior from Thomas Jefferson High School for Science and Technology in Northern Virginia. For my project, I developed Dynamic Operating Room Companion, or DORC for short, which is a system that monitors surgery in real time and goes through frame by frame and evaluates the surgeon's actions in every single frame and uses that information to flag surgical errors in real time to help out surgeons in the operating room. So, this project was actually inspired by my cousin in India who died of a preventable brain surgery error, um, which was caused by a surgeon who was likely really stressed or overworked. And also based on a few conversations that I had with my sister, where she told me about how she and her friends were really, really stressed because they were getting less face time with their teachers and less time in the lab. So they were feeling less confident about their abilities to perform surgeries in real life. So um, after these conversations with these two really important women in my life, I decided to create a system that would help them by analyzing surgical videos in real time and by providing a guiding, helping hand for surgeons for them to do their jobs of saving patients' lives. So, in order for my system to be useful, it had two major requirements. So, it needed to be accurate. It needed to accurately identify the surgical phase or surgical action in each frame, because if it's not accurate, then it wouldn't really be of much help to a surgeon in the operating room. And it also needed to be fast because it needed to be able to flag errors in real time, because a lot of times in these surgeries, they're fast-paced environments. So if the flag was delayed by even a few seconds, then the results could be disastrous because it would be too late to prevent the actual error. So I used a data set called the Colic 80, which is a set of 80 full length, fully annotated gallbladder removal videos. And I analyzed this data set in two major steps. So, the tool recognition, which is the act of going through frame by frame and identifying the location and the presence of each tool in each frame. And there is phase recognition, which uses the data from the tool recognition, from the positions and presences of each tool to output the surgical phase or which action the surgeon is doing. So, in order to perform the tool recognition task, the network needs to observe each frame and search within this really large frame um, for some smaller surgical tools within the frame. And that's like a lot of search area to cover, which can be really computationally expensive. It can be really slow for the system to do in real time. So the standard model, the standard system that most researchers use for this task is called fast RCNN, which tries to do this task, searching the larger image for smaller components, using something called a region proposal network, which uses a lot of time expensive matrix calculations to do this task. But the thing is, this network is really, really powerful, but also really unspecialized. So when we try to apply it to our specific problem, we can actually notice that for what we're trying to do, if you look at the frames, the background of the frame is almost entirely pink because it's going to be like the gallbladder, the liver, the stomach walls. So that's entirely pink, while the tools are black, white, and gray. So we can segment this image based on the pixel color using a support vector machine, and we can sort of filter out all this pink, and then we're just left with regions that must be the tools. So this takes a lot less time than a region proposal network. And now we move on to phase recognition. So this tool recognition process gives us some time series data, which it evaluates the presence and location of the tools in each frame. So it'll give us a series like frame 1, frame 2, frame 3, etc. And while this is going on, we're also going to have a phase value, frame 1, frame 2, frame 3, etc. So in order to map between this tool data, this observed tool data, and this hidden frame data, we're going to use something called a hidden Markov model. which uses probability rules, like and some machine learning in order to learn the patterns in the observed data and try to map it with features from the hidden data. So in order to improve upon the standard hidden Markov model, I also implemented some linear temporal logic and some Bayesian probability rules, which brought my overall accuracy up to 93.5%, which is 3.5% higher than the state of the art of 90%. And using these speedups from the tool recognition part of the project, I was able to get the project running in 60 milliseconds per frame, which is 5 times faster than the current state of the art. So in the future, I hope to improve these results further, and I hope to get to 97% accuracy by using more advanced models and by also trying to implement some 3D localization based on robotic signals instead of just 2D location from the camera. Thank you so much for your time.